So good morning, everyone. My name is Amit. I am a principal engineer at Cisco Meraki in Bangalore. On behalf of the rest of the iMobile ACM chapter team, Sandeep, Jagdish, Shogato, and Rohit, I would like to welcome everyone to this webinar. This is a webinar that we have been doing regularly, and even though we have not been able to do it at a very fixed cadence, but we have tried to do 2 to 3 webinars in a year. Let me give a brief introduction of iMobile for the benefit of our first-time attendees. The iMobile ACM chapter is the India chapter of ACM SIG Mobile and was founded in March of 2019 as a community of researchers and practitioners in India with an aim to develop a greater passion for systems research in the country and in adjoining areas, right? So while adhering to the global charter of SIG Mobile, so it is an ACM chapter, so we are bound by the ACM rules and regulations, and we are tied to SIG Mobile. So the chapter wants to focus on a lot of platform research in theory and practice of all areas related to mobility of systems, users, data, and computing. Work on the evolution of portable computers and wireless networks, convergence of mobility, computing, and information organization, and overall improve access, services management, applications for mobile computing and communications, right? Initially, when we started off, we had an in-person workshop, but since then the pandemic hit, and then we have not had an in-person workshop. We might have it sometime in the near future, but as of now we are doing regular webinars just like this one. These are usually held once a quarter and are free for people to attend. You don't need any kind of membership to attend, but I would still request people who are not members of iMobile to just get a membership there. It's the membership itself is free. If you go to our website, if you just search for ACM iMobile, you'll find that, and you can go ahead and register yourself. With this, I would like to hand over to Shogato, who is an assistant professor in the Department of Computer Science and Information Systems at BITS Pilani, Goa campus. Shogato has been leading the effort of arranging the webinars and kind of shortlisting speakers. And I will now hand it over to Shogato to introduce the speaker for today's session. Shogato, over to you.
Thank you, Amit, and good morning, everyone. Welcome to this webinar. So it gives me immense pleasure to welcome Dr. Vireshwar, who will be presenting today. Dr. Vireshwar is an assistant professor in the Department of Computer Science and Engineering at IIT Delhi. He's done his BTech from the Electrical Engineering Department at IIT Delhi, and he's done a PhD from Virginia Tech in the CS department. He has been a postdoc at in Purdue University before he joined back IIT Delhi as a faculty. So Dr. Vireshwar's interest includes anatomizing the communication protocol employed in cyber-physical systems for security and privacy vulnerabilities, and then mitigating them with innovative defensive mechanisms. So with this, I'll like to warmly welcome Dr. Viresh, who will be taking over next. Over to you, Dr. Viresh.
Yeah, thanks for the warm welcome, Sagata, and yeah, thanks, Amit. As Professor Sagata mentioned, my research area involves investigating security issues in cyber-physical systems, and in this talk, I will focus on the resource-constrained systems. So basically, resource-constrained IoT devices and their security. So is my screen visible in the right mode? Okay.
Yes, it is.
Yeah. Okay. So let's first look into what we consider the IoT space when I'm talking about the security of it. So this is what I consider as Internet of Things, is that there are some nodes in any network, and these nodes are not only communicating with each other, but they are also affecting, in some sense, the physical environment around them. So for instance, if we consider a smart city environment, let me try the pointer. Yeah. So if we consider a smart city environment, let's say it is a smart electric grid, smart water treatment, smart road transportation, so anything related to a smart city can be considered as a set of connected nodes communicating in order to realize some activation or some sensing of the physical environment. We can say similar things about a smart home environment with the smart cameras, the smart sensors, door sensors, smart plugs, smart bulbs. And more specifically, smart transportation will involve cars or vehicles communicating with each other and probably communicating with the infrastructure, which means lights or even roadside units, even individuals. And then, of course, the smart robots, which include not only industrial robots, but also drones, for example. So with this definition of Internet of Things, so people have been investigating different types of attacks, and of course, they have found a variety of attack surfaces. And in many cases, they have come as a surprise to the user community. So not to probably the research community, but to the user community, it has come as a surprise. So for instance, when an attack was launched on the Ukraine's power grid, and the entire Ukraine, a large part of Ukraine was in dark, people were surprised that such a cyber attack could be launched. Similarly, when the Mirai botnet was utilized to launch denial of service attack on a variety of web servers, where this Mirai botnet actually exploited the CCTV cameras to launch the attack. So then it was a big issue. Similarly, hackers have shown compromising vehicle running on a highway. And then, of course, smart cameras have been easily hacked, and there have been many such cases. So my research actually involves discovering and mitigating these kind of security and privacy issues arising of these kind of cyber attacks. And in this talk, so the goal is cyber physical systems or IoT devices which are resource constrained. Now, just to highlight the implication of the resource constraint, so let me just talk a little bit about some preventive techniques that we utilize in conventional computer security. So in conventional computer security, so there are typically two types of security properties that we would like to provide. So one is secrecy or confidentiality, which means hiding the information that is being communicated. Or the second property is the authenticity or integrity, which means verifying who the sender is and ensuring that the message that the sender is sending to a receiver has not been modified during communication. So if we look into both these properties, so these two properties could be achieved either in the symmetric key setting, where the sender and the receiver both have the same secret key, symmetric key, or in the asymmetric key setting, where each of the senders and each of the receivers, they have a pair of public and private keys. Okay, so these are the two settings in which both the properties could be provided. Now, if we look into the confidentiality, so there are block ciphers, there are string ciphers, which could provide confidentiality in the symmetric key setting. And if we look into the integrity property, so we have cipher-based message authentication codes or hash-based message authentication codes. So these are some of the ways in which you could provide integrity in the symmetric key setting. Now, if you look into the public key setting, so for confidentiality, the protocol is popularly known as the public key encryption. And for providing authenticity integrity, the protocol is probably popularly known as digital signatures. Okay, so with this background, a very quick background of symmetric and asymmetric cryptography that is typically utilized in computer security. Now let me try to give you some numbers. So if I run these cryptographic algorithms on a typical laptop, a little outdated 9th gen i7 processor with 16 GB RAM, so good enough power for running these kind of cryptographic protocols. So these are numbers after running these cryptographic protocols on a laptop with this configuration. So if you see the encryption algorithm, So let's look into one symmetric event and one asymmetric event. So if you see the running times, so you will see that it is below 1 millisecond for symmetric key, but for asymmetric key, it is around 5 milliseconds. So of course, at least one order of magnitude higher than what you would have seen for the symmetric key segment. And similarly, if you see the length of the block which is generated after the conversion of plain text to ciphertext in this encryption algorithm, so the block length is also very large in terms of the asymmetric key segment. Okay, so what we try to focus here is the execution time here and the block lengths. Okay, so they are of course more than a few bytes. Now for the authentication algorithms or integrity providing algorithms, so if you look into the CMAX, cipher-based max, or HMAX, hash-based max, you see they are still in sub-millisecond, so below 1 millisecond. But if we look into digital signatures, whether it is RSA-based or whether it is elliptic curve-based ECTSA, so they are of course above millisecond. And if you look into just the digital signature, which provides authentication using RSA, so this is at least you can say that it is 2 orders of magnitude more computationally intensive than a symmetric key based authentication. Okay, so 2 orders of magnitude more complex. Okay, so now that we have this idea that symmetric key cryptography is more efficient, asymmetric key cryptography is probably not more efficient, but there are of course more properties in asymmetric key cryptography that we would like to of course utilize, and the difference is from 1 order of magnitude to 2 orders of magnitude. Okay, so now let me give you some numbers about what we typically see in resource constrained IoT devices. So if I look into a typical laptop or typical desktop on which I'm trying to implement these cryptographic algorithms, so there the clock frequency is around 2 gigahertz or so. The packet length, the communication protocol, whichever is being utilized, so it is self-sufficient. It has sufficient bandwidth. We can use very large packet lengths, and of course, it has a large RAM in which I could do a lot of computation. I could store a lot of things and retrieve a lot of things. But if I look into a typical IoT device, so there the clock frequency is significantly lower. So a couple of orders of magnitude lower. Okay, so now you are seeing at least 2 orders of magnitude lower in this example. It could be different for different IoT devices. The bandwidth that is being utilized in terms of bytes, so the numbers are in terms of bytes here. So the bandwidth will be also something which will be 2 or 3 orders of magnitude lower than what we would see for a typical computing platform, typical computers or typical laptops. And then the RAM that will be utilized, it is significantly constrained. It is probably many more orders of magnitude lesser in this case. Okay, so before, so now that I have highlighted that the typical IoT device is significantly constrained in terms of resources, which means computational resources, which means communication resources, and third is the storage during the computation. So in all these 3 aspects, these typical IoT devices significantly constrained, a few orders of magnitude more constrained than a typical computing platform. And therefore, it is very difficult to run the asymmetric key cryptography on a typical IoT device. Okay, so that is given that if you look into an asymmetric key cryptographic protocol, it is very, very difficult to run on a typical IoT device. What remains is the symmetric key cryptography. So there also there are significant challenges in implementing them on these IoT devices, but at least it is feasible to implement this symmetric key cryptography on these IoT devices. So I hope this whole discussion is clear at this point that IoT devices are significantly constrained. Asymmetric key cryptography is out of question. but symmetric cryptography is possible on these type of devices. So any question at this point? Because then I will change gears and talk a little bit about other things.
Vireshwar, I had a quick question.
Yes.
So the communication limitation, is it intrinsic to the resources available in the IoT devices, or it is just that they tend to send packets or pieces of information which are very small compared to, say, a regular computer?
Yeah, so that's a good question. So I think it is a mixture of the two. So what will happen that if you utilize a communication protocol which provides a large bandwidth, then the energy that you will require to utilize that communication protocol, that will be also very high. Now, if an IoT device utilizes such a communication protocol, it has to be probably somehow powered by electricity. So it cannot typically be battery powered, otherwise it will drain within a few hours or so. That is what we will see for any of these devices that are battery powered, but they utilize some communication protocols which are which provide high bandwidth. So larger bandwidth with larger packet sizes requires the IoT devices to spend more energy on transmitting packets. So therefore, if in a typical IoT device setting, for let's say smart ring, smart watch, so there typically the design that is preferred is that we use communication protocols which are lesser in bandwidth, which require lesser packet sizes, and which ultimately results into spending of lesser energy from the device side. Any other question? Okay. So now let me now come to the main part of this talk, where I would demonstrate a few attacks and then, of course, a few attacks on resource constrained devices. One will be an illustrative wired communication protocol, and the other will be an illustrative wireless communication protocol. So for the wired communication protocol, I will be talking about controller area network, CAN bus, which is typically utilized in automobiles. And for the wireless communication protocol, I will be talking about Bluetooth low energy, which is very widespread these days. So most of the technologies which used to have conventional Bluetooth is now utilizing Bluetooth low energy. I will talk about that. Okay, so now let's move to the first part, the wired communication protocol part, which is the controller area network bus, CAN bus. Okay, so if you look into this whole idea of a smart vehicle or a modern vehicle, so these vehicles are being developed in two directions. So one is the autonomous aspect of the vehicle, which is being improved. So you might see facilities like cruise control, where your accelerator, your brake, your engine, all of them are talking to each other and ensuring that whatever speed you set for the vehicle continues to go at that particular speed. So that is the intelligent part, that is or the autonomous part that is being added to these vehicles. And of course, completely autonomous vehicle is also in the line, and similar ideas apply there, where you have many other subsystems within the vehicle talking to each other to provide a completely autonomous vehicle. But in even a simple, any intelligent feature that you see in modern cars, that we are indicating as an autonomous feature, at least for the discussion in this talk. Now, if you look into what facilitates these autonomous features, is this electronic control units, so ECUs. So for every subsystem, we have one ECU controlling it. So for in a typical vehicle these days, we have more than 100 ECUs. So your steering wheel has an ECU, your brake has an ECU, the doors have ECUs, lights have issues, engine has multiple ECUs, and every subsystem has different types of ECUs. And these electronic control units, they communicate over the communication protocol, which is called controller area network CAN. Okay, so when I said intelligent feature as cruise control, so that there I meant that these different ECUs connected to different subsystems are communicating over this CAN bus and facilitating this intelligent feature. Okay, so that is one aspect of vehicle. The other aspect of vehicle that you may also realize that is getting very popular is the connected aspect. So the vehicles are now being connected to external entities. So of course, you are easily able to connect your mobile phone to your car to play some music and stuff. So that is there for a very long time. But now there is Wi-Fi connection possible in your cars, in modern cars, and also there is cellular connection possible, and you could see live streaming of IPL matches inside your car. So all this communication is facilitated through a node, which we'll refer to as onboard telematics unit, OBU, and this facilitates this connectivity of this vehicle to the outside world. Okay, and of course, we would like to move in this direction of both so autonomous direction and connected vehicle direction in order to provide a variety of facilities to the users, and especially towards reducing the number of accidents that can happen on the road. Okay, but now that these two aspects are coming together, which is the autonomous aspect and which is the connected aspects, so now they are bringing security threats to the vehicle. So the vehicle was, when this CAN bus was designed in 1980s or so, there was no concept of connected vehicle. And therefore, the designers never thought that we will need any security of the messages which are communicated over this CAN bus. So therefore, they have the design is in such a way that it is very difficult to ensure security of messages on the CAN bus. But now we are moving in both directions. So we are connecting vehicle to the outside world, to the internet, and making it a part of Internet of Things. And we are also adding more features, which means more control through these messages. So now if someone finds a bug in any of the communication protocols, for instance, cellular, Bluetooth, or vehicle to infrastructure, or their implementation on the onboard unit, or the protocol which implements all of this or facilitates this connection to the external world, so then it is problematic because there is no in-vehicle security. So there is no, so if an attacker could bypass the security which is present in these kind of communication protocols by default, then it can get access to the CAN bus of the vehicle. And because the CAN bus does not provide any security protocol to be implemented there, so now the user or the attacker could have a large unlimited access for maneuvering the vehicle. So for instance, it can disable brakes, it can control the steering wheel, and it is not that this attack is unknown. So people have researchers have shown this kind of attacks, a possibility of these kind of attacks on a variety of vehicles coming from these top manufacturers. And in many cases, the devil is in the detail of implementation, where the implementation that I'm referring to is something which is related to the communication protocol, so how that protocol is implemented in the onboard unit which is installed on these vehicles. Okay, so now just to give you a quick feel of what researchers had shown when this area became hot. So the area of looking into security issues in vehicles. So these researchers, they showed, they showed that, okay, yeah. Yeah, so in this demonstration, you see that the researchers were able to control the vehicle from a remote location, and they were able to change the speedometer value, control door locks, disable brakes, steering wheel controls. All of that was possible, and this was possible because there was some vulnerability in the entertainment system, which I am referring to as onboard telematics unit, and the way it was connecting to the internet. So the implementation bug was exploited to launch this kind of attack. Okay, so now let me just tell you the reason why this attack happens. So we have this V2X modem. So we have onboard telematics unit, so OBU, and it has two interfaces. One is to the outside world, which is through this vehicle to everything modem. And then one is to this CAN bus, controller area network bus, which actually connects all these different subsystems. So body may have one ECU, brake may have another ECU, engine may have another ECU. So all of this, they are communicating over CAN bus, and then this OBU is making or facilitating connection to this CAN bus through this V2X modem. Okay, so you can remotely connect to this different or control these different subsystems within the vehicle. And if this OBU is compromised, then there is nothing stopping the attacker to control all of these different subsystems, because there is no security, there is no encryption, there is no authentication. Okay, so what is the way to go? What is it that these automotive manufacturers are doing? So they are installing what is called intrusion detection system. So of course, if you cannot prevent attacks, then you will have to go ahead and try to detect attacks. And the reason why you cannot implement defense here is legacy issues. It is very difficult to change CAN bus because of its robustness to electromagnetic interference and other properties. So people are sticking with this CAN bus, but because CAN bus does not facilitate encryption authentication, they cannot prevent attacks. So the way to go is intrusion detection systems. So now this area has been looked into for quite some time. So people have been coming up with attacks, and then corresponding intrusion detection systems have been developed to detect those attacks. And this thing keeps on happening, and more attacks and more defenses are being developed. Okay, so now what we did, so until now whatever I talked about is what is in the existing literature. So now before I tell you what we did, any question about this idea of security in automotive domain? Okay, so now that we look into this intrusion detection system, so this is a very interesting area. So intrusion detection systems, so they are getting better and better. So you can consider an intrusion detection system as a machine learning model, which is doing just a simple binary classification. It is looking into some network traffic. It is saying whether it is a benign network traffic or it is a malicious network traffic. Okay, so simple ML model doing this binary classification. Now you know that ML has been developing for the last decade, and there have been very advanced ML models that provide very high accuracy, and it has been applied to intrusion detection systems as well, and people have been able to achieve high accuracy. But then alongside this area of machine learning, there is another area which is also getting very popular in the security community, which is the adversarial machine learning, where people have developed methods to bypass the machine learning models. Okay, so reduce the accuracy of the machine learning model. So the attacker, so this is the adversarial setting. So ideally, the machine learning tries to increase the detection accuracy. The adversarial machine learning type of work shows that there are ways in which the attacker could manipulate the whole system and reduce the accuracy of the machine learning model. So that is what we did. So we acted as an adversary, and we said that, okay, these automotive manufacturers, they are using intrusion detection systems in their vehicles. So can we bypass their intrusion detection systems using some adversarial machine learning techniques? Okay, so that was our goal, that we want to use some adversarial machine learning technique and bypass the intrusion detection system that are typically utilized in vehicles. And we were, of course, successful in doing that. So let me try to run this. Yeah. So here in the screen there are multiple windows. So on this side you have the dashboard of a vehicle. So this is a little bit old vehicle, but at least the concept is the same. So it is canvas facilitating communication. So here is our attack setup. There are some Arduino Uno boards which are actually emulating the resource constrained behavior of the devices which can be called electronic control units. Okay, so this is so Arduino Uno boards are very resource constrained boards, and what we are trying to highlight is that even when these resource constrained devices are there, they can still launch very effective attacks on the canvas network. And then we have some an oscilloscope looking into the communication protocol and some circuitry, and then some interface where we are looking into the network traffic, the logs related to the attack, and logs related to the intrusion detection system which is running on the vehicle. Okay, so let me now run again. Yeah. So what we are doing is we are seeing that on the dashboard we have 700 revolutions per minute, and we are looking into the network traffic corresponding to the message, which means the dashboard has to interpret it as 700 revolutions per minute. Now we are also starting our logs for the attacker and the intrusion detection system. Okay, so now in the first stage of the attack, where the attacker is learning how to launch the attack, you don't see any change. So it is still 700 revolutions per minute, but the attacker is being trained to launch an attack. And when the attack is launched, then you see that the dashboard has starting to show some numbers. So 7,000 revolutions per minute is something that is typically not possible in these kind of old cars, at least. So this is definitely a malicious number that is being shown to the driver over the dashboard, and the corresponding traffic is shown here. So the attacker is manipulating the whole network in order to launch this attack. And then this intrusion detection system, so it is running some counter, and if that counter goes above some threshold, which in this case was 200, then it would have raised an alarm that an attack is being launched on the vehicle. But we made sure that the counter that was being utilized in this intrusion detection system, so that remained very small, and therefore no alarm was generated as a result of this attack. Okay, so the attack has been known for quite some time. The contribution in this work was that the intrusion detection system that was running was not able to detect the way the attack was launched. And the reason why it was not able to detect is that we utilized what I'm referring to as adversarial machine learning technique to bypass the detection of the intrusion detection system. Okay, so that is basically the demonstration of the attack. So I will not probably go into the details of the attack, but if there are any questions about this attack, I will be happy to answer.
So in this attack, did the actual engine's RPM increase, or it was just a display thing that it tried?
It is just display. Okay. So the engine, so we are not directing these messages towards engine. So of course you could identify.
You could do that, right? I mean,
yes,
that
yes.
is the bigger danger, right?
Yeah, that is the bigger danger. You could always do that. So this is good for the demonstrative purpose, that you could now launch this attack without doing any disruption to your car. Because you are running these experiments for a year or so, you don't want your car to break. So you try to, so if you see the automotive work, people typically try to show this kind of attack, because there is no harm here. It is just dashboard which is showing some numbers. But so it demonstrates that engine can be controlled, brake can be controlled, anything can be controlled.
So in this case, how do you actually connect to the bus, to the CAN bus?
Yes, so in this case, we connect physically. So in this case, if you see our this Arduino Uno boards are connected to the CAN bus physically, but our threat model says that because of this connected nature of vehicle, it is possible that some vulnerability could be exploited in the communication protocols, and the onboard telematics unit could be compromised, and then the attack could be launched from there. Okay. Any other? I think there are 2 chat messages.
No, so we just there's no question yet.
Okay.
You have around 20 minutes.
Data set. Sir, can you tell us the data set used? Yeah, so the data set, we did not use any standard data sets, but if you look into the existing literature, so there are some automotive data sets, attack data sets, which you could utilize. In this work, we used our own setup to generate traffic and then launch attack on this real automotive, the real vehicle. So we did not utilize any existing data set to demonstrate results. But of course, there are existing data sets. Okay, let me move forward.
Viresh sir, we are at 11:40, so we have around 15-20 minutes.
Yeah, so I will probably conclude in 10 minutes, and then we will probably have a few questions. Okay, so let me probably not talk about the defense. So of course, defense says better machine learning models, better intrusion detection systems, and we have proposed some ideas about how we could improve those intrusion detection systems. So now let me quickly move to the other part, which is compromising a device utilizing Bluetooth Low Energy. Okay, so now if you look around yourself, you will see that Bluetooth Low Energy is something which is the most prominent communication protocol these days. So whether it is a smart home, whether it is wearables, whether it is healthcare related issues, whether it was the Arogya Setu app that you had used, all of them utilized Bluetooth Low Energy protocol. And the share of Bluetooth Low Energy has been increasing, and the share of the conventional Bluetooth has been decreasing constantly over the years. And now the share of Bluetooth, conventional Bluetooth, is close to negligible. There are some, of course, applications like headphones which are still using conventional Bluetooth. Okay, so now what can go wrong in this setting? So your mobile phone communicates to your smartwatch over Bluetooth protocol. So now if you receive an OTP related to your bank transaction on your mobile phone. So you get it through a cellular network. So hopefully the cellular network is secure. So you get it on your phone securely, but then you are sending it to your smartwatch over Bluetooth. So if Bluetooth communication protocol is not secure, your OTP is not secure. So of course, people can eavesdrop on the OTP that is being communicated. The attacker can eavesdrop. The attacker can have illegal device access, which means issue related to authentication. And of course, again, issue related to authentication, where some data manipulation can happen, which means the actual value that, let's say, a glucose meter is sending to your mobile phone is one, but the attacker manipulates that value. And then the user can be manipulated to take a medicine or leave the medicine based on the number that they might see. So there are a variety of things that can go wrong if Bluetooth can be compromised. Now we looked into the Bluetooth domain, and it has been looked into for quite some time, for decades. For at least 2 decades, people have been looking into security vulnerabilities. And they have looked into a variety of threat vectors. But we investigated a very unique threat vector. So we said that we will investigate the reconnection procedure, which means that once the device and the, let's say, mobile device and your smartwatch, they are connected and they are paired, then what happens is that either your smartwatch is switched off, or the mobile device and the smartwatch, they become very far, and therefore they become disconnected. But remember, they are still paired. Okay. And then what happens is that when they come back in close proximity, they reconnect. And so although in the first time when you are pairing and connecting, so there you utilize OTP and different type of techniques to make sure that you are securely establishing the connection between the two devices. But during the reconnection, it is automatic. There is no user involvement in this reconnection. So what we wanted to do was look into this reconnection procedure and see if there are some security vulnerabilities there. And why would the security vulnerabilities be present there? And the reason is that a smartwatch is a resource constrained device. Designers always use some excuse to do some trade-off, and typically the corners which are cut are related to the security. So it is possible that there could be some issues in the reconnection procedure. So we wanted to do that, and of course we found some vulnerabilities. So we did a formal analysis of the BLE reconnection procedure. We used a tool to do that analysis, and we found a few design vulnerabilities. And then in that analysis, we also actually found one implementation vulnerability. So design vulnerability means that there is some lack of security protocol which had to be implemented but which is not there. So it is the design issue of the protocol. But implementation vulnerability means that the security protocol is there, but it is not implemented correctly, and therefore the authentication or any other security properties could be bypassed. So our attack, we named it as Lisa, and I will give you a demonstration of it as well. But let me just tell you about the impact of it. So we were able to find that implementation vulnerability in Linux devices, which were implementing Ubuntu, and the Bluetooth stack was BlueZ. And we were able to also find security vulnerability, the same security vulnerability in Android and in iOS. But Windows was, interestingly, the operating system which did not have this security vulnerability. So Windows stack of Bluetooth was did not have that security vulnerability. So we were able to demonstrate that our attack works against the large range of devices. So of course, the impact is in billions of devices. So now let me just demonstrate the attack here. So So here, what you are seeing is a smart ring, which is paired with a companion app in an Android phone. Okay, so the companion app shows the values from the smart ring, and this smart ring could be utilized to track your sleep activity and other things. You see the battery level is 43%. The smart ring is 43% charged. Okay, so now we go ahead and launch attacks. So now what we do is we utilize the Bluetooth development board to generate packets, which will be now received by your mobile phone. And during this reconnection procedure, so now see it is reconnecting. So during this reconnection procedure, your mobile phone, the Android phone, will now get connected to our attacker. And now we will start sending messages to this companion app. So we will, the first message is that the spoof message is battery level is 0. So just now you saw that it was 43%. And the second message is charging is complete. So both messages are being sent. They of course do not make sense. How can the charging be complete, but the battery level is 0? But we are demonstrating that these are the messages coming from an attacker, and they're not coming from a benign device. So now the attacker could send any message to the companion device, and it will show that device. And you see that it is still the same device which is paired. So now why this is possible? Because this is the authentication was bypassed. So there has to be an authentication between the smart ring and the companion app on the Android device. But because that authentication was not implemented correctly, the attacker was successfully able to launch this attack. Okay. Yeah, so of course, we had, before publishing this work, we had talked to Google, Apple, Intel for fixing the vulnerabilities, and they had fixed the vulnerabilities, and then we published this work. Okay, so any quick question about this work?
So was this a BLE protocol vulnerability or the implementation vulnerability from the OS?
Implementation vulnerability. So finally, what we exploited was an implementation vulnerability in some of these implementations. So it was not but I guess it originated from the design of BLE. So basically, BLE standard provides a few options. So there are some secure options, there are some insecure options. So what happened was that these three went with the insecure option, and this Windows implementation went with the secure option. So what I would say is that the BLE, the reconnection procedure, which is standardized, so it has this combination of secure and insecure options. And if while implementing, if you are not careful, then you can definitely implement something which is wrong. Any other question?
So in this case, you're demonstrating this with the Aura ring, right? But this could have been done with any device.
Any device using Bluetooth Low Energy protocol.
Right.
Question. Yeah, I'm sorry if I missed this. No exchange of any two input to a device. There's a handshake confirming the ID of the two devices and the protocol for this reconnection procedure. Yeah. So yeah, so that's a good question, Ashish. So yes, sir. So typically, when devices communicate initially, they do pairing, and there you put up OTP and stuff, and that is very secure. So people have been able to show that they are secure. Of course, there have been some attacks, but overall, that communication is secure. So what we analyzed was the reconnection, not the first connection, but the reconnection part. Can the regular DOS and DDoS attack scripts work? Probably for the previous, this question is probably for the previous work, attack scripts work. I'm not very sure about what the question is about. How can we mitigate this data set? Yeah. So of course, there has to be some patch, and so really from your side you can't do much. Apple did patch it in iOS 13.4 version. Now probably you are using 14 version, so you should not have this issue. So this attack now will not be successful on your device. But in the previous version, it was successful. Okay, so let me just quickly go through some defense recommendations. So in the defense recommendations, so there are typically three recommendations that people give, and I'm just reiterating those the defense recommendations. I'm not going to the detail of the defenses that we developed against these two attacks, but these are very generic recommendations. So prevention, detection, and response. So these are the typical three pillars on which any defense stands. Okay, so you try to prevent attacks. So of course, it is important for security experts to develop cryptographic protocols which could be implemented in these resource-constrained devices. Both attacks that I have showed you, they could be launched because security was either not present or bypassed, because these were resource-constrained IoT devices. They cannot implement cryptographic techniques, or they cannot implement the secure version of cryptographic primitives. Okay, so that is the reason why these attacks were possible. So of course, if you are using a system, you should have a security policy. The attack will ultimately happen on your system, so you should have some security policy guidelines which will ensure how your systems are protected, how your how detection will happen if the attack somehow bypasses your prevention mechanisms, and how you will recover after the attack. So there has to be a security policy in place. And of course, some lightweight cryptographic techniques have to be developed where the computational and communication and storage requirements of these protocols are lesser. And then, of course, the basic thing that a user can do is continuously update your devices. So that is something that I'm sure you are doing. In the side of detection, so we are in the age of ML, AI ML. So we have to be very careful about adversarial ML as well. And the research has to be done in that direction. So we are looking into that direction, how these ML models can be made robust against adversarial ML assisted attacks. Okay, so that is definitely a research area. People are looking into those kind of things. What existing system managers could do is conduct runtime assessment, analyze offline data. So of course, there has to be runtime IDs which must be running, but there should also be something which can do in-depth analysis of the data in the offline manner. And sometimes some manual investigation is also required to actually detect some attacks. And then response has to be multi-tiered. So while the attack is happening, you should be able to isolate the attacker. You should be able to raise an alarm, initiate some kind of recovery mechanism, and then finally figure out a way to mitigate the vulnerability. So to summarize, we talked about the constraints in IoT devices which make them vulnerable to attacks. And then we talked about two illustrative attacks, and then talked about a few defense recommendations. And that is the end of my talk. Thank you.
Thank you, Viresh. Very interesting, very insightful. There are a couple of questions that are there on the chat.
Yes.
Can
you suggest some good lightweight cryptographic techniques can use ECC and ECDS in resource-constrained devices? Yeah, so that's a good question. So can we use ECC on resource-constrained devices? Okay, so let me just show you these numbers here. So if you look into these numbers, if you use symmetric key cryptography to do authentication, you have sub-millisecond numbers. But if you use ECDSA, it is definitely 1 order of magnitude more computationally expensive. So depending on the IoT device, you may or may not be able to use ACC. Of course, it is always preferable to use public-private keys to do authentication. Yeah, so in many IoT devices, it is not possible to even use ECC because you see 1 order of magnitude is not a small difference. So are BLE attack scripts publicly available? Yes, so if you look into the work that researchers have been doing, even if you can follow my webpage, so we have published that work, and we have also released some of the code that we utilized for attacking the BLE protocol. But again, so these attacks will not work on the existing versions. On older versions, it used to work. How could we? Yeah. So I think this attack, this talk is already recorded. I will also share this slides with Professor Saugata, and he might share with all participants. Is blockchain feasible in such scenarios? So basically, blockchain is so blockchains are so it is a very different type of security mechanism. It is not applicable everywhere. But let me just say that blockchains utilize hashes. So SHA-3 based hashes, and it utilizes digital signature. You can think of some combination between this number and a digital signature, probably, let's say CDSA, so this number. So it is a combination of two numbers here, 0.1 and 2.0. So blockchains are also not very lightweight, so they're also very computationally intensive.
Thank you, Professor Vireshwar. Thank you once again. I think there are lots of questions still, but this was overall very insightful. Thank you for being a speaker out here, and I'll let Amit and Shodip to take over and say the final words and thanks.
Yeah, thank you.
Hey, thanks, Vireshwar. Thanks everybody for joining, and hopefully this was a very nice session. I myself asked a lot of questions in this. This is very interesting and something that impacts probably way more people than we initially can understand from it, because it's these days everywhere you have IoT devices. Right? So yeah, Sandeep, any final words?
Yeah, so thanks, Vireshwar, and thanks to all the participants. The talk was very interactive. Yeah, that's all. Thanks.
Bye, everybody. See you in the next webinar.
Yeah.
Thank you. Bye-bye.
Bye.